Word break problem. Have you ever faced the word break problem in a tech interview? This is one of the most popular Pattern Mastery 100 LeetCode questions, appearing everywhere from Google to Facebook. More than 35% of candidates stumble here because it tests your ability to combine dynamic programming and hashing under pressure. Mastering word break is not just about solving one problem, it's about unlocking a core interview skill. So, let's break it down together and ensure you never trip over this one again. Let's break down the word break problem. We're given a string S and a list of words, word dict. The challenge is, can we split S into a sequence of dictionary words? For example, if S equals cat, sand, dog and word dict equals cats, dog, sand, and cat, can we build S using just these words, without reordering or skipping letters? We want a Boolean answer, yes or no. Now, let's assess the complexity. The brute force approach would check all possible splits, exponentially slow. But we can do better. If we use dynamic programming, we can store sub-problem results. For every index in S, we ask, can I split up to here using the dictionary? A hash set gives us O1 lookups for dictionary words. Edge cases, empty string, should return true. And if word dict is empty, we should return false. Next, let's structure our solution. We'll build a DP array, DP, where DPI is true if S, I, can be broken into dictionary words. Set DP0 equals true as the base case, empty string is always breakable. For each position I, check all possible partition points j before I. If DPJ is true and SJI is in word dict, set DPI equals true. Finally, return DPLens. Approach, dynamic programming. Time complexity, O(n squared). This line defines a solution class. In Java, we place our method inside a class like this so it can run on platforms like LeetCode. Here's our main method. It takes a string S and a list of words called word dict, and it returns true or false depending on whether S can be split into valid dictionary words. We store the length of the string in n. This helps us avoid calling s.length repeatedly and makes the loops easier to read. This converts the word list into a hash set. Why? Because checking if a word exists in a set is fast. So instead of slowly searching a list, we can quickly ask, is this word in the dictionary? Pause here. This is a performance helper. Now we create a Boolean array called DP with size n+1. DPX will mean, is it possible to break the first x characters of the string into valid dictionary words? It's like a checklist for every cut position in the string. This sets the starting point. DP0 means the empty string is always breakable, because we haven't chosen anything yet, and that's a valid starting state. This outer loop moves I from left to right across the string. Think of I as a potential starting cut where we try to begin matching words. This is a smart shortcut. If DPI is false, that means we cannot successfully break the string up to position I, so there's no point trying to form words starting from I. We skip ahead immediately. Small pause, this helps efficiency. This inner loop tries every possible ending position j after I. So we're exploring all substrings that start at I, Si, j. This is where the O(n squared behavior comes from. We try many start/end pairs. Here we build the substring from index I to j and check if it exists in the dictionary set. In plain terms, is this chunk a real word we're allowed to use? If that substring is a valid word, we mark DPJ as true. That means, we can successfully break the string up to position j. It's like placing a checkpoint flag at j saying, yes, we can reach here using valid words. This closes the loops. By the time we finish, we've marked every position that can be reached by chaining dictionary words. Finally, we return DPN. That represents whether the entire string, all n characters, can be broken into dictionary words. This closes the method. And this closes the class. Final wrap-up. And that's how this algorithm works. It first sets up a reachable position checklist with DP. Then it scans forward and marks new reachable positions whenever it finds a dictionary word chunk. Efficient, simple, and elegant. Test case check. Word break using dynamic programming. Let's test our function using this input. S equals LeetCode and word dict equals LeetCode. The string represents the full word we want to break apart, and the list contains the valid dictionary words we're allowed to form. Here's why the solution works. Our DP array DPI tells us whether the substring S0:I can be segmented using the dictionary. We start with DP0 equals true, meaning the empty prefix is always valid. Then, for every index I where a valid segmentation exists, we try expanding forward to every j greater than I. If the substring Sij is a dictionary word, we mark DPJ equals true. And that's exactly what our program outputs. True. The result matches the expected output, confirming that the DP logic is functioning correctly. Wrap up. So, our implementation is correct. The algorithm successfully checks whether the entire string can be segmented into valid dictionary words, efficient, accurate, and reliable. Approach: recursion plus memo. DFS time complexity, O(n)². This line defines a class name solution. In Java, every program needs a class as a container, and this one holds our word break logic. Here we define the word break method. It takes a string and a list of dictionary words, and returns true or false depending on whether the string can be split into valid words. This line converts the word list into a set. A set allows us to check if a word exists very quickly, which is important for performance. Here we create a memo array. This stores results for positions we've already checked, so we don't repeat work. Think of it as a notebook where we write down answers we've already figured out. This line kicks off the recursive search starting from index 0 of the string. All the real work happens inside the DFS helper function. This line defines the recursive helper method. It tries to decide whether the substring starting at index I can be broken into valid dictionary words. This is the base case. If we've reached the end of the string, it means everything before it was successfully split, so we return true. Before doing any work, we check the memo array. If we already know the answer for this index, we reuse it. This is what prevents exponential slowdowns. This loop tries every possible next word starting at index I. It explores all substrings that begin at I, which is why the time complexity can reach O(n)². Here we check two things. First, whether the current substring exists in the dictionary, and second, whether the rest of the string after it can also be broken successfully. If both checks succeed, we store true in the memo array and immediately return. This means we found a valid way to break the string. This closes the loop that tries all possible word splits. If none of the options work, we store false in the memo array. This tells future calls that starting from this index will never succeed. This closes the recursive helper method, and this final brace closes the class. Final wrap-up. And that's how this algorithm works. It first sets up a fast lookup structure and a memo table, then recursively explores word splits while caching results to avoid repeated work. Efficient, simple, and elegant. Test case check. Word break using DFS plus memoization. Let's test our function using this input. S equals apple pen apple and word dict equals apple pen. This string represents the full sentence we want to break apart, and the dictionary contains the valid words we're allowed to use. Here's why the solution works. We explore the string from left to right using recursion. At each position, we try every possible substring as start end. If that substring is a valid dictionary word, we recursively check whether the rest of the string can also be segmented. And that's exactly what our program outputs. True. This confirms that our memoized DFS logic correctly identifies valid splits and handles repeated patterns efficiently. Wrap up. So, our implementation is correct. The algorithm successfully determines whether the string can be segmented using recursive search with memoization, efficient, accurate, and reliable. Word break problem. Let's do a recap. Ever hit the word break problem in an interview? It's one of those dynamic programming classics that separates good candidates from great ones. This challenge isn't just about splitting a string, it's about recognizing patterns, using efficient lookups, and proving you can think dynamically under pressure. Breakdown recap. We began with the goal. Given a string and a dictionary of valid words, can we split the string into a sequence of dictionary words without reordering or skipping any letters? Essentially, we're checking if the entire string can be built piece by piece using only the given words. Assess recap. We compared brute force and dynamic programming approaches. Brute force tries every possible split, exponential and inefficient. The DP method, on the other hand, reuses previously computed results to make smarter decisions, while hashing gives us instant dictionary lookups. Together, they form an elegant O(n)² solution. Structure recap. The plan was simple but powerful. We used a DP array where each index represents whether the substring up to that point can be segmented into valid words. Starting from an empty base case, we built our solution step by step, checking all possible word boundaries along the way. Implement recap. We implemented the DP logic with efficient hashing and ran it on LeetCode. The code executed smoothly without any errors, correctly determining whether the string can be segmented. Check recap. We verified the logic by testing with sample inputs and confirmed that the output matched expectations. The algorithm passed all test cases successfully, confirming the DP table and logic worked exactly as intended. Closing insight. The big takeaway? Mastering word break teaches you how to merge dynamic programming and hashing, two of the most important tools in problem solving. Once you see how they work together, You'll not only solve this problem with confidence but also spot the same pattern in dozens of future challenges.